Buen día a todos, agradecerles y darles la bienvenida, compartir este espacio. Somos los amigos argentinos de la Universidad Hebrea de Jerusalem, quienes estamos muy agradecidos de poder hacer esta primera actividad conjunta con el ITBA. Agradecerle a Mario Bolo, a quien le voy a dar la palabra en un ratito, y agradecer muy especialmente a Moshe Shenfeld por estar esta mañana con nosotros desde Israel y poder compartir este espacio junto a todos nosotros sobre Machine Learning, que va a ser el tema del encuentro de hoy. Así que bueno, toda rabá, Moshe, Baruch Habá, y le paso la palabra a Mario para dar inicio a este encuentro. Muchas gracias.
Bueno, buenos días a todos. ¿Se me escucha bien? Ok, perfecto. También yo les agradezco a todos por estar acá. Quería hacer una breve presentación de Moshe. Como ustedes habrán visto en el flyer, Moshe está haciendo su doctorado hoy en día. Bueno, él tiene una triple especialización en ciencia de la computación, física y matemáticas. Está haciendo su doctorado en la Escuela de Ciencia de la Computación de la Universidad Hebrea de Jerusalem. Pero además, en este momento, Moshe ha ganado una de las becas que otorga Apple anualmente para hacer investigación en temas relacionados con Machine Learning. Esa es una beca muy particular porque Apple la otorga muy poquitas, son 15 becas en todo el mundo nada más, a investigadores que se consideran líderes emergentes en temas de Machine Learning. La investigación que está haciendo Moshe tiene que ver con el tema de la privacidad de la información en Machine Learning, tema muy importante porque a veces en los sistemas que usan este tipo de tecnologías hay datos que son sensibles y que quedan potencialmente expuestos. Así que seguramente Moshe nos va a hablar de todo eso. Al margen de su actividad académica y de investigación, Moshe ha tenido también una amplia actuación en la industria, ¿no es cierto? Ha trabajado mucho en la industria, y va a ser interesante que él nos cuente cómo se relaciona el tema académico con el tema de la industria, digamos, cómo en su vida él ha complementado los dos aspectos y cómo se interrelacionan entre sí. Los micrófonos van a estar apagados, los micrófonos de los participantes, durante la sesión, pero les pido por favor que si tienen preguntas, las hagan a través del chat. Vamos a dejar un espacio al final de la charla para poder responder las preguntas que ustedes puedan tener. Vayan poniéndolas en el chat, ¿no es cierto? Y si quieren pueden hacerlo en castellano, yo lo traduzco, no hay problema con eso. Así que bueno, sin más, Moshe, now it's all yours.
Thank you. And since I have no idea what Mario told you about me, I don't confess to anything. Everyone hears me well?
Yeah, yes.
Okay, thank you. So thank you, Mario, Marisa, everyone, Laura, for organizing this event and inviting me. I will try to spend the first few minutes justifying the idea of me taking an hour of your time, and then the rest of the time actually speaking about the subject that we chose together. So my name is Moshe Shenfeld, and I'm 38 years old, and during my adult years, I moved back and forth between academia and the industry in both capacities in a relatively algorithmic and machine learning to some extent orientation, but still I touched the subjects from several aspects. So I got my bachelor degree in Hebrew University before I started working. Then I started working and in parallel got my master's degree. And then about a half a year ago, I decided to leave my position. I was a team manager and in Mobileye. I will speak about it in a minute. And I decided to focus on my PhD. A few years ago, I had a conversation with my brother. He's a mathematician, relatively in a very theoretical aspect, even within mathematics. And he told me that sometimes he has a hard time justifying his work because he feels like even if he will solve the biggest problems in his small field, it's not clear if it will ever, if and how it will ever help the human race in any capacity. And then we had a discussion thinking about what is the process. So imagine you want to justify every scientific progress done, at least in the, not in the humanities, but in the life science. So you want to justify any progress by showing the full set of influences, which leads from this to an actual elevator or car or airplane or any kind of real world use that is somehow based on it. And we were thinking how challenging it is to show for a theoretical theorem in math. What is the sequence of papers that quoted that paper and then were quoted by several papers later, and then someone from the industry read it, and so on and so forth, until we see the real world use of it. I think it's very challenging, and I don't think I am a professional in this field, so I can actually show a full sequence of links from theory to application. But since I have some experience in both sides of the chain, in a sense, I can say something about it, I think. So what I would try to do in this talk is speak a little bit about the things I did in Mobileye, the company where I worked in for the last 8.5 years, and then a little more about my experience in academia and about research, and to try to show how these things relate to each other, even though the things I did in Mobileye in industry were not directly the same kind of things that I did in the academia, but they're all related in many ways. So let's start by Mobileye. Mobileye is an Israeli company. It is we're now developing autonomous vehicles, but it all started in something called ADAS. ADAS is Advanced Driver Assist Systems. Basically, any vehicle that you have today that has some capability of saving you from making a mistake, whether it is beeping if you're swerving off your lane without signaling, or intervening and braking when you're getting too close to someone, or warning you if you're too close to a pedestrian, or any kind of intervention from just beeping to actual affecting your driving. That's called ADAS. In a sense, you can think of it as the very first steps in a ladder leading to a full autonomous vehicle at the end. And many of the vehicles that have these capabilities are based on the Mobileye technology. So Mobileye is an Israeli company. All of its business is just selling a chip with the algorithm that can detect the potential danger and warn or make a decision of what should be done to the car manufacturers. And when you buy a car, you get it. And during the last 5 years, Mobileye has joined the race of actually aiming to get to a full autonomous vehicle. We have many testing vehicles driving all around the world. And eventually, at some point, when autonomous vehicles will be a thing, Mobileye will definitely be at least one of the main competitors. Actually, what happened about 5 years ago, Mobileye was acquired by Intel, and just a few days ago, Intel re-released, it's called a spin-off, re-released Mobileye to become a public company again, and it was the IPO was in NASDAQ just last week, and it was the biggest IPO in this year because, you know, the economy is not in best condition, so a lot of companies avoided trying to start in this year, and they did, and were relatively successful. So it's an interesting company. The main sensor Mobileye uses to understand the world around it, when you think about it, all of the things I mentioned, from just warning someone that something might be problematic till the full autonomous vehicle, they're all, in a sense, points on a scale where you need to understand the world better and better as you move on the scale, and make decisions that are more and more free from human intervention. So the level of confidence you need in order to beep is not that high, even if sometimes you missed a beep, or sometimes you beeped when there was no danger. It's not a terrible problem. And if the vehicle is fully autonomous, any decision it makes has to be accurate with very, very high probability. But they're all the same. Sense the world around you, understand what's happening, and then make decisions based on that. The main sensor used by Mobileye is a camera. When you think about it, an image, a camera image, is a 2D projection of the 3D world. The world has 3 dimensions, has depth, but when we look at an image, we don't see the depth, right? Something is lost. And if we don't have any extra information, we cannot distinguish between something that is small and close or big and far. So one of the main challenges in Mobileye is understanding the depth of objects and the 3D model of the road and of the movement of the vehicle and that kind of thing based on these 2D images. And I say images in plural because A, sometimes we have more than one camera located on the same vehicle, and B, even if you have one camera, since it's a video, and a video is effectively a sequence of images, each one taken in a different time frame, so you can combine the information you got from different images and different timestamps to understand something about the way the world looks. In general, in Mobileye, the way the teams are organized is every team is responsible for a certain type of object. So there's a team responsible for dealing with vehicles, a team responsible for dealing with pedestrians, with lanes on the road, with the edge of the road to understand what's the area where you can't drive, and so on and so forth. All of these teams need to understand what they see in the image, and they will apply some neural network or any kind of learning algorithm to understand, oh, this part of the image, I see a vehicle or a human being, etc. And then they need to issue some depth-related questions. Okay, so how far is this person from me? And that will depend on the model of the road, etc., etc. So our team was responsible for providing the basic 3D modeling of the road for the whole company. What does the academia have to do with it? So it's interesting. We applied many of the things that you actually learn in academia and in various ways that are distinct from each other. One of the fields that we used is called projective geometry, and I understood from Mario that in ITBA you have a research group dealing with it, which is a relatively small and niche kind of research subject. In several words, it's a mathematical field, and it deals with, as the name hints, the projection of things from one dimension, from a n-dimension world to an n-1 plane. Usually we use it for 3 dimensions projected to 2 dimensions, 3D being the world and 2D being the image, but it can be anything else. It's the kind of thing that almost none of the people who came from academia were familiar with more than just maybe taking one course. And we had our Bibles that everyone had to learn when he got into the team. And it was an interesting experience for me to see papers and works that were not quoted extensively because this is not such a large field, but for us were the very basis on which all of our work was done. And I sometimes thought about, like, wouldn't it be nice if we would just be able to visit sometimes these researchers and tell them, you know, hey, I don't know how many quotes you have, and I don't know how many people in academia spoke with you about it, but the industry, at least part of it, is really relying on you. Even after you measure something using the models of the projective geometry, you still have noise. Anything that happens in the real world is noisy. We know that. So when you work in the clean mathematical model, so you can say, okay, these points behave according to this equation, and then I can extract some value. But then for any kind of real world application, even if it's not in the industry but in the lab, once you start measuring something in the physics lab, you don't get points, you know, all the electrons behave exactly the way you expected them based on the laws of electrodynamics and the charge, etc., etc. You get a noisy signal, and then you try to clean it, you average, you do all of the statistical things you need to do in order to actually get a good, trustworthy signal. In the industry, it is even more present because, unlike physics, many of the things that occur in the real world are much more complicated. I mean, again, it's all physics. There's nothing else in the world in a sense, but you can't choose a toy model to implement in the lab, in the real world as you do in the lab. In the lab, we can say, okay, we will make sure there's no other equipment that interferes with this phenomena, and we'll use only a simple beam, and we'll use, I don't know, a light with a certain range of wavelengths, etc., etc. And then you come to the real world, and you can say, okay, vehicles must have this color, or pedestrian must work in this way. Things happen the way they are, and you need to deal with it. And when you have an algorithm that runs several times every second, because every time a frame arrives, you need to analyze it. For every vehicle that was sold, and we're speaking now of tens of millions, I think we're approaching 100 million over the years, each one driving probably an hour on average a day. So that's a lot of times these algorithms run, and you need to have very high probability that it will provide a response that is at least highly accurate, if not perfect. And there, what happened was we found ourselves doing things that are, most students meet it learn it in bachelor degree, or at most at the first year of master's degrees, classical statistical models, linear regression, things like that, nothing out of the ordinary. But we found out how much you need to dig in and understand why exactly is this theorem correct, and what exactly is the noise model that you must assume in order to achieve this result, etc., etc. A lot of things that when you learn as a student, there's just a set of assumptions, and you don't feel anything towards the assumptions. Okay, you assume it's Gaussian, you assume it's not Gaussian, they're IID, they're not. You don't feel the weight of this assumption. The assumption was given by the TA because this way it's easier to solve the question, and you can get it in time for the deadline. This is the kind of things that happen. And then in the real world, it actually matters. And sometimes it is IID and sometimes it's not. And when it's not IID, you need to understand the implications and so on. So another interesting experience I had during the years in Mobileye was to see what happens when you take something that is very very familiar. Most people are familiar with it. Most employees came with the relevant knowledge. It's widely used, and you would think that, oh, this is not a problem. This is something we know. And then you realize there is a long way from proving a theorem under assumptions and providing conditions, etc., etc., till the point someone can use it in the real world and actually confidently say if indeed this is a good enough rule for the application. If not, how can we change it, etc. I think one of the best examples for the difference between academia and the industry and the process that goes from moving ideas from one to another is the difference between the criteria for getting a paper accepted to getting a patent accepted. One of the ideas we had in our work revolved around extending a common mathematical tool in computational geometry. And when we completed the development, we realized that along the way, we came up with a relatively general claim that might be useful also in the academia. And we started checking the option of whether we can publish it. Then, as you can imagine, there are complications because it happened in the industry. There is the issue of IP, and Mobileye needs to protect its knowledge, etc., etc. And we went to discuss it with the legal department. And generally speaking, the answer for this kind of problem is, well, if it's patentable, then Mobileye will patent it and then publish it. And as we were going through this, we realized that the criteria for getting a paper accepted to a journal and the criteria for getting a patent approved by the department that's responsible for it are almost mutually exclusive. So if you prove Riemann's hypothesis or the theory of relativity or anything big that is important enough to get you a Nobel Prize or a Fields Medal or anything like that, you will never be able to patent it because the rule is so large, so general, that we don't want to stop people from using it in any other way. If you want to patent something, it has to be very specific with a very specific type of usage. I take common physical laws and use them, apply them to create a piece for an engine that will work slightly more efficiently because the way the fuel will be moving will have less friction or something like that. No new rule, nothing changed in our understanding of the physical world, but I managed to apply it in a slightly different way, and now everything is working slightly better. Then you can easily get a patent. Try to publish a paper about it. No one will let you publish this as a paper because it's not interesting. It's a very specific kind of usage. The other way, on the other hand, if you prove something general about any manifold of this sort can do this or that, all of a sudden you can publish the paper. A patent you won't get for it. So in a sense, I think that explains what is the major difference between the academia and the industry in this sense. The academia is trying to understand something about the world. The world is around us exists even before the human race ever evolved. And there are rules that govern it. And in a sense, we can imagine it as like a platonic world. The truth exists even before we observed it. And academia, science, is trying to increase step by step our understanding of that truth. It can be mathematical, pure truth, and it can be something physical about the world. But in all cases, you want to know, okay, this is how an atom is constructed. And this is what determines if two molecules will combine or not, etc., etc. If and how will it be used? Will someone be able to build a elevator from it later on? Maybe yes, maybe not. We try in academia to ask the questions as though we don't care if and when and how someone will use them. It's not really this way. Many people in academia do care about questions that have some implications about the world, but it's not the focus of it's not their main goal. On the other hand, in the industry, even the parts of the industry that strongly rely on science, they don't care about the most correct version or the most general version or the best understanding of the world. They have a different function they're trying to optimize. The elevator needs to work. The car needs to drive itself. The airplane needs to take off and not require too much maintenance. And in a sense, the research aspect of it in the industry is how do we take these big ideas and implement them in the real world to the specific usage that we need. With that insight in mind, I will try to tell you a little bit about my research, remembering that even though most of my focus these days is about the theoretical aspect and finding general claims, my experience in the industry leads me to always think about the ways it can influence the world, and I will try to mention it as I go along. So my main research field, the one where I started, is called differential privacy. Here's the problem statement. Say we have a data set of patients that were treated in a hospital. And we have a lot of information about them, not only about the kind of treatments they got and the conditions they had and the results of the tests and the way things changed with time. We also have some background information about them, their age, their weight, their height, number of children, etc., etc. This is very useful information. We can use it to deduce what kind of treatments are more helpful for certain conditions, what kind of background conditions will increase or decrease the chance of some illness to appear, that some treatment will work better for people with a certain properties, etc., etc. I assume it's very clear why this kind of research is important. On the other hand, we don't want to allow people to identify from the data set any personal information. If I was treated in this hospital and I have a certain medical condition, I do not want the researcher observing this data set to be able to deduce that me, personally me, have a this or that condition. Now you might say, okay, what's the problem? I will remove the name, I will remove the ID or any formal identifying properties of the person, and I'll release it to the researchers. The problem is that even the rest of the information might allow any person viewing the data to identify me. Think about combining the area you live, the age, the weight, the height, maybe the ethnicity, maybe which country were you born in, etc., etc. All of these properties are important because people from certain ethnicity might have a genetic tendency towards this or that, etc., etc. So every piece of information here is important, but combining all of them, we might be able to identify someone. You might think this is far-fetched, and I'm a bit too worried. So here I'll give you an example. About 15 years ago, for several years, Netflix ran what they call the Netflix Prize. It was a competition for machine learning experts where they provided a data set of people and the movies and series they watched, and they asked the competitors to predict which movies will the people want to watch later? Or to be more precise, given the recommendation, will they choose to watch that movie or not? Obviously, the goal was to improve their recommendation system. The data set included for each person a fake ID, so nothing that was related to any formal identifying information, just some running number. A list of all the movies and episodes it watched with the dates. I don't remember if it was the exact date or the range of time when they watched it. And maybe one or two more pieces of information, such as whether they were their gender or the country they lived in, but very, very basic. Now, take a moment and ask yourself, given this data set, can you imagine how you will be able to detect, even for one of the people in this data set, which person is it? Give it assign a name and say, this is the person that this line in the data set is referring to. My best guess is most of you think about it as practically impossible, unless you're familiar with this case. But what happened in reality was that people managed to solve it and identify some of the people in the data set. And the way they did it was combining the information from this data set with another publicly available data set, which is IMDb. I don't know if you're familiar with it. It's the Internet Movies Database. It's a public website where people, basically there's information about movies, movie stars, etc., etc. And people can open a profile there and just give scores to movies and create a watch list, etc., etc. So what these researchers did was they compared the two lists and they looked for people that had all of the, or most of the public information in most of the movies in the public database, also in the Netflix line. Now, imagine someone watched in Netflix a movie that he's ashamed of sharing. Again, this example is not that terrible. It's usually the movies, there are ones that even if you won't want to share, it's not so terrible if anyone knows, but it could have been worse. So he would watch on Netflix a bunch of movies. Some of them he will publicly write about in his blog, in IMDb, and the rest he won't. But now by combining the two databases, all of a sudden you can identify him. Now, what I like about the story is that it gives you an example of how many ways are there to identify a person in a database, even when it seemingly there's almost no information about him that can lead to identifying him. The fact that this problem occurred led people for many years to deal with the tension between releasing information that is statistically significant for the use of the public, mainly the researchers, while at the same time protecting the privacy of the elements in the database, usually people in the database. And about a little over 15 years ago, a new idea came and a new field in a way was created, and it's called differential privacy. And here's the idea in a nutshell. Say I want to know what is the average salary in Mobileye. But no one wants to tell me what is his own salary. You might think this is not a problem. Here's an idea. I take a small calculator. I put some tape on the screen so no one can see what's happening. I pass it between all the employees and ask each one to write plus his salary. Then when we get to the last employee, we divide it by the number of employees. I remove the tape and I see the average salary. And I know that the average salary is, I don't know, 15,000 shekels. And I didn't learn anything about anyone in particular. But now someone joined the company, so the average probably changed. So I repeat this whole process. Now I know the average with this person and without this person. Problem is, once I know these two numbers, I can deduce what is the exact salary of this person. So I want to create a method to understand what is the salary, the average salary of the company, without identifying one person, even if there are some changes, or I can ask about some subset. So here's the solution. Let's assume the calculator I have, instead of providing me the exact number, the average that it's calculated, it adds some random number with a certain variance. Now, Mobileye has, give or take, 3,000 employees. And let's assume for simplicity that the maximal possible salary that even the CEO gets is, I don't know, 300,000 shekels per month. So that means that the effect that one person has on the salary, on the average, is at most 100 shekels. Shekels is the Israeli currency, right? Because in the most extreme case, everyone earns 0, and then the new person earns 300,000. So the average without him was 0, and with him is 300,000 divided by 300, so it's 100. 3,000, so it's 100. So if I add noise that scales with standard deviation 100, that means that on one hand, when I compare the two numbers, the number of the average with that person and without that person, the effect of the noise added in the two cases is probably larger than the effect this specific person had on the average. On the other hand, the amount of noise I added is relatively small. It scales like the effect of one person. When we perform statistical studies, we need to have a large enough sample size such that changing one person won't change by much our conclusions. Otherwise, we're very sensitive to any kind of sampling noise. So the idea is, if you want, you can add a little bit of noise to your data, to your results, such that it is enough noise to mask changing one person, but on the other hand, it's not so much noise that the accuracy is already significantly affected. And what it means is that the amount of noise that is added masks the question whether any person even participated in this data set or not. So imagine if we go back to the hospital example, if the two worlds, one where the whole data set was released and one where my specific record was swapped with someone else, if we cannot distinguish between these two worlds because of the added noise, so there's no way anyone can tell anything about me. They can't even tell if I was in the data set, not to mention if I have this condition or not. So if people can't tell if I was in the data set or someone else, they can't say anything about me. And if the noise that was added is enough to mask the effect of one person, they won't be able to tell if I was in the data set or not. Of course, on the other hand, we need to make sure we didn't add too much noise such that the responses we provide are meaningless. Even though this is a relatively new field of research, it was already widely applied in many places. The most famous one is the US Census. It's their Bureau of Statistics. Once in 10 years, performs a very large research where they survey. They have a few researchers, a few surveys. One, they survey practically all U.S. citizen, at least that's what anyone that lives in the U.S., another one where they survey a very large sample of them, and they release the information, aggregate. So they tell you, in this county, this is the number of people who live, and this is their age distribution, and this is their weight distribution, and this is their ethnicity. Like they have certain percentages that are black and Hispanic and white, and all sorts of pieces of information. And when you think about it, it's also dangerous, because imagine there's a neighborhood with only one Asian person, and you, in the Bureau of Statistics, will publish the information of what is the average salary of Asian people in this neighborhood. Well, the average salary of Asian people in this neighborhood will be the salary of this particular person, because there's only one Asian person in this neighborhood. And the result will be that effectively the government told everyone how much this person earns. And it can be many other things. So you must protect the privacy of the people that were surveyed in some way. And this year, it's performed every 10 years. So it was 2000, 2010, and now 2020. And so first of all, it took a little longer because of COVID. So a few things were delayed. And now they're in the process of analyzing the data and publishing it. And they decided to do all of it using the differential privacy toolkit and framework. A lot of large companies use it. So you might think, oh, this doesn't make sense. It's against the interest of Google or Apple or Microsoft to maintain the privacy of their users, because that's how they make the revenue. But in fact, when you think about it, it's not exactly their interest. Google does not care about any one of us in particular. It wants to be able to direct better ads towards us, or get us to buy some of their products or things like that. But they don't really care who I am. So from Google's perspective, or from Apple's perspective, if there was a way to learn about the distribution, to learn about the type of ads that there is the highest chance that I will click on without learning about me, they don't care that I browse this website or that website, that I use my computer in these hours, that I type in that way. These are all clues that might help them better target me with ads or anything like that, but they don't care about the content. Think about autocomplete or autocorrect. The techniques where the algorithm either detects error in your language and corrects it, or even guesses the rest of the sentence for you. In order to learn it, it must read a ton of information. So imagine Google, they would need to read all of our emails, but they don't really care about the content of my email. They want to know how likely is this sentence compared to that sentence, so they can choose the most probable end last words or last few words. But they don't want to know about me. So if there's a way for these companies to learn what's important to them without affecting our privacy, it's easier for them, because then they don't need to worry about data breach. Then they don't need to worry about the government not allowing them to use some of our information. They don't need to worry about the government trying to force them to give them some information. They don't need to worry about a employee stealing information that he shouldn't use. They don't know the information. They know only what they need to know in order to improve their tool, but most of the private information remains private. And specifically, I'm familiar with Apple, which recently created a very large research group, and they have many of their researchers that publish the important papers in this field are now part of the research group by Apple, and I got their scholarship. I am officially an Apple Fellow, and part of it is also getting involved in research with the field. There's, by the way, even one company that actually provides it as a service. If you are a company that has some data and needs to publish it, or a hospital, etc., so there's a company that already provides this as a service to other companies, and obviously most of their employees are scientists from this field. But it's probably just the very early days of a whole industrial field that will evolve from these academia research related topics that we are discussing these days. I will just use 5 more minutes to touch on one more thing that I'm dealing with, to show how many potential ways are there to use these ideas. So one of the things that people discovered only in the last, I think, 8 years is that protecting the privacy of the data is not only helpful in case of sensitive information, it is useful even when you don't have any sensitive information in your data, because it helps you avoid overfitting. So overfitting is a general term that people use to describe the phenomena where we try to learn something about the population, about the distribution. We sample a sample set out of that population. We try to better understand this data set, and by that generalize to the population. But there is always some probability that by trying to improve our explanation of the data set we got, we will actually start tailoring our hypothesis to the data set, and in a way that has nothing to do with the real world. That's what overfitting is. And one of the very interesting things that we found out was that if you learn in a way that maintains the privacy of the data, with high probability you will not overfit. Why? Because if you maintain the privacy of the data, you don't know what elements were even in the data set. So if you don't know who was in the data set, of course you won't be able to come up with an hypothesis that is tailored to the data set, which means that differential privacy is just one aspect of a much larger idea of trying to learn in a way that focuses on the important things and doesn't know too much, or doesn't learn too much about the technical small details, whether they are the private details or just irrelevant details. And in a sense, differential privacy can be observed as one reason to try to separate what's called the hay from the chaff, the important stuff from all the noise around it. If people ask me, where did I enjoy, which years did I enjoy more, or which kind of job did I enjoy more, it's hard for me to say. I mean, I think what I enjoy most is going back and forth between these fields. I think our generation is to some extent unique in the amount of opportunities that people that learned our kind of subjects have to move between academia and the industry. Like for many, many years, and even in these days, in many fields, these are totally completely different options. You either try academia and it's a career and that's where you focus and you're completely detached from the industry or from the real world applications of whatever it is you do, or you're in the real world and nothing theoretical ever applies to you. And in this era, the high-tech boom, the fact that computers are becoming just more and more involved in any aspect of our life, and it means that more and more people that understand how to model, whether it is the computers themselves or the physical world and the way that computers can affect it and can communicate with it, have the ability to move between them and understand, in a sense, what, at least generally speaking, what does the chain leading from the theoretical mathematical paper all the way to the elevator, what does it look like? And taking part in one of the links along the chain and maybe moving to links that are more theoretical and less theoretical along the way, I think in many ways we're very lucky to have this opportunity. And if there's anything I would want people listening to this talk to take home message, is that I strongly recommend that you try to deepen your knowledge and understanding in both directions. Whatever it is that you're doing, try to learn a little bit more about how people apply it, and try to learn a little bit more about what is the theory that is behind the things that you do. Because both directions, what you understand allows you to do a much better job in the thing you do and move afterwards to one direction or another if that's what you wish. I think that's it, and I'm be more than happy to answer some questions if you want.
Thank you very much, Moshe. We have one question, but let me, I just want to make one comment myself. You know, in Argentina, we have a census, a permanent census of socioeconomical data, where, for instance, the families are asked about salaries. And many people are afraid that the government can use that to identify you and perhaps use that for tax purposes. So I think that these technologies in which you're now involved about protecting data for specifically for machine learning, but I guess that will work for data analytics as well. This is very interesting, and that specific application is very interesting. And your last message, I think, it's fundamental. I mean, in many cases, the researchers have the trends, or they are biased towards just pure science, you know, and perhaps they are ignoring the potential applications in real life. And on the other hand, people at the industry used to disregard, you know, but at least that happens in Argentina. I don't mean to say that that's something universal, but they disregard the theoretical research as something that's very far away from the real world. So I think that one very valuable thing that comes from your conference is the linkage between the two worlds. There's as you said, there's a continuous chain of events that carries us from pure research, pure science, to the practical applications. And it is very, if one can have the chance, as you had, to move back and forth from pure science to the real world applications, that's great. But even if you don't have the chance, I think that it is important to keep that in mind, that maybe sometimes things that seem to be very, very theoretical can have an unexpected application that you cannot imagine at the first time, no? But we'll have a very probably an application.
I think the best example is the math field of number theory, which for many years was considered one of the most theoretical and detached from the real world fields. And then all of a sudden cryptography arrived, and it became one of the most applicable fields. So,
Absolutely.
you know, and it's decades, and it was unpractical, considered unpractical.
It was kind of a game, a mathematical game. But now, of course, this is the basis of modern cryptography. So you're absolutely right. Well, we have one question by Antonio Di Pasco. He's asking, does Apple better protect data than its competence in any way?
I mean, I assume the competitors. Well, I don't work for Apple, and I can't say anything about what happens in the real world. I do know what are the kind of questions that researchers that work for Apple are focused on, and I assume they deal with these questions because they want to apply it. And it's the kind of examples that I gave before about learning from your information without getting your information. So imagine just one example. We want to train some neural network. You know, anyone speaking about learning these days is discussing in one way or another deep learning, neural networks. And neural networks are trained by applying gradient descent. And the gradient is estimated based on data. That's where the data comes in. We have some function, some loss function, and we have a set of parameters, and we differentiate that function given these parameters, and we make a step in that direction. And how do we differentiate? We don't know the true distribution, so we use data to estimate it. Imagine a world where the company never gets the data even out of your computer or your cell phone or your watch or any kind of electronic device. All it does is send a question, a query to your device and tells you, here's the gradient. I'm trying to estimate it. Give me some information. And you can give the information in a way that barely helps anyone trying to learn about your data anything, but on the other hand, is sufficient, once combining a lot of people, to improve the model. And I know this is the kind of research that is done these days. And in a world where all of learning by the big tech companies will be done that way, that means that your private data will never even move to the cloud if you don't want. The website you browsed in, and where did you go, right? Imagine your geolocation, your phone and your watch have all this information. All of this data will never be sent anywhere. It will only be used on device to change the model in some way and then send this change to the cloud to help it improve. This is the kind of research that is done these days. To say how much of it is already running now on your iPhone and what exactly happens in a different company, I don't have the knowledge to say, but I'm sure if this research is done, it's because they want to use it as soon as possible.
Well, he is thanking you very much. I don't know if anyone has another question. We have time for one more question. I don't know. In fact, your conference was very, very clear, Moshe. So it seems that there are no more questions right now.
Okay.
So I think we're done. Thank you very, very much for an excellent talk today.
Thank you for this opportunity.
Mario, por mi parte, bueno, solamente agradecerles en nombre de los amigos argentinos y de la Universidad Hebrea esta excelente predisposición que hizo posible el encuentro. Gracias, Moshe, bueno, gracias especialmente Mario, gracias a Antonella Giordano en la Coordinación para la Cooperación Internacional y, bueno, y a Germán Moyano, director de Relaciones Internacionales Universitarias. Espero que este sea el primero de muchos y grandes proyectos que vinculen al ITBA con la Universidad Hebrea. Muchísimas gracias a todos. Toda Rabá, Moshe.
Gracias a ustedes.
Thank you.